What do we do to affect solubility? So again, solubility is how much can dissolve. Can we change the amount that can dissolve? We can. There's a couple of things we can do depending on what kind of solute that we're talking about. And so the first one we're going to talk about are solid solutes. So solid solutes. So for example, salt. You can throw salt in water. Sugar. Can we change how much salt or sugar can dissolve in a liquid? And the answer to that is yes. And one way that we can do that is by increasing the temperature. If we increase the temperature, we can get more of the solute to dissolve. So higher temperatures increase solubility. And you may have some experience with this. You may not. But if you want to make a sweet drink and you want to make it super sweet, you throw the sugar in as the drink is at room temperature or even warm. If you're making like fresh brewed tea or something else, you throw the sugar in when it's warm because more sugar will dissolve in it. If you throw the sugar in after you've iced it down, you get very little sugar to dissolve into it. And so if we want to get more to dissolve, we simply increase the temperature. Gaseous solutes. So for example, oxygen, okay, in water. This would be an example of a gaseous solute. So fish live in the water. They don't breathe water, they breathe oxygen. There's oxygen dissolved in the water, and the fish breathe that oxygen through their gill system. And so gaseous solutes can also be influenced by temperature. But in this case, it's the reverse. If you increase the temperature, you actually get less and less gas in the liquid. And your probably experience here is with Coca-Colas. If you open like a 2-liter bottle of Coke, when you're done, if you don't finish the drink, you seal it back up and you put it in the refrigerator. You don't leave it on the countertop, because if you leave it on the countertop, you may not know why you do this, but the solubility decreases as the temperature of the Coke increases. The solubility decreases, and less of the carbon dioxide will stay inside the Coke, which makes the Coke go flat when you let all the carbon dioxide out. Lakes and streams can also have an adverse effect if they get too warm. The oxygen content in the water decreases. There's not enough oxygen in the lake or stream or river for the fish to breathe, and they suffocate. You have a fish kill. And so sometimes there's an issue of thermal pollution. It's not really pollution in the sense of something bad in the environment, but it's thermal pollution where some factory or power plant releases heat into a stream because they use water to cool their factory, and they let this hot water into the stream, and that hot water can adversely affect the environment around that factory where it decreases the oxygen content in the water, and then there's some fish kills around there. Typically, there's a lot of rules and regulations that prevent that from occurring, where the plant has to ensure that the temperature comes back up to, or comes back down to a reasonable temperature before they discharge it back into a lake or stream or a river. But it used to be a big problem before we got a little more wise on our environment. High pressure increases solubility. So here's your Coke example again. When they bottle a Coke, they really pressurize the can of Coke. They put a lot of carbon dioxide in there because they want a lot of carbon dioxide in the Coke to make it bubbly and fizzy and make it taste good. And so increasing the pressure increases solubility. When you open the Coke, you hear it fizz out, and a lot of that pressure is released, and a lot of the Coke, not the Coke, a lot of the carbon dioxide that's dissolved in the Coke, since the solubility goes down, it undissolves itself, and you see all the bubbles come out of the Coke. And so gaseous solutes, the high pressure increases solubility, low pressure decreases solubility. For the gas solutes, higher temperature decreases solubility, and for solid solutes, high temperature increases solubility. So you need to know these relationships, if you will. You will be asked about them for sure, potentially in just a concept idea and potentially in a mathematical situation as well. Okay, how about factors that affect the rate of solvation? So this is not how much, but this is how fast. And these should be easy. I think, like I say, I think we did a lab early in the school year on these. So how fast, that's an O there. How fast something dissolves. There's a couple things that we can do to make things, or 3 things we can do to make something dissolve faster. One thing that we can do is we can increase the temperature. If we increase the temperature, something will dissolve faster. We can shake it, or what might be termed agitate it, or stir. You could use the word stir it. And lastly, we can increase the surface area or change the surface area. These are the things that will increase the rate of solvation. I'm looking at it from the point of increasing. So doing these things increases the rate of solvation. So increase the surface area will increase the rate of solvation. And so if you think about them for a second, they can all make logical sense. So the dissolving process, once again, is you've got this ionic compound that's bound together, and the water needs to come in, attach, and move out. And so if you increase the temperature, well, the water simply moves faster. And that allows the water to move in faster, attach, and move out. They also have a little more energy, so their strength of attachment is a little stronger. And so that would increase how fast the water moves in, moves out, attaches and dissolves the solute. Shaking and agitating, the same thing. If you're shaking and agitating, you're causing water molecules to collide with the solute. They can attach and pull away as well. Increasing the surface area might be a little bit more difficult to understand, but let's try and do that here. So let's say we have this ionic compound, and I'll do a 4x4 cube of it. Now this is just two-dimensional. It should be three-dimensional, but here's two-dimensional. If you look at this cube two-dimensionally, the only water molecules, let's say that these four here are on the inside. The only particles that water could attach to and pull out are the ones on the outside. So the water could attach to these four, and then those 4, 12, 13, 14, 15, 16. There are 16 atoms or ions exposed. There are 12 atoms or ions exposed to the water to be able to be attached. Now, if I break this crystal, and now it looks like I've got a crystal here, I've got two smaller crystals, and they're separate. Well, now my water can attach to any one of the ions at any time, so all of them are exposed. And so now all 16 could be solvated simultaneously. And so by increasing the surface area, or by breaking something up, you increase surface area, then you're increasing the amount of ions that could be solvated simultaneously, and you increase the rate of solvation. So if I had a cube of salt versus granulated salt crystals, little granules of salt, and I had the same amount of salt, the salt crystals would dissolve faster than the salt cube. They would both dissolve if we weren't exceeding the solubility, but this would dissolve at a faster rate than this. It would be dissolved in a minute versus maybe 5 minutes for the crystal. And so those are some factors that affect the rate of solvation.